Okay, section 5.6 is about degeneracy. This is a really neat theoretical topic and also has practical implications. So I actually want to start with the figure from our book. This is on page 253, figure 5.6. So many optimization software programs show an iteration history. So this is the number of iterations on the x-axis, and then this is your objective function value on the y-axis. And you can ask, you can figure out how to get MATLAB to do it, go to the linprog or intlinprog help and turn on that option. And first of all, is this a maximization or a minimization problem here? Well, it looks like because the objective function values are rising, it must be a max. Oh yeah, actually he tells us that right there, it's a maximization problem. And so we're seeing some progress. But what's interesting here is we don't always make progress. Here's where there's a plateau, another plateau, and so on. We eventually, and maybe this is the end, could be that you've terminated here, or you can also, many software codes give you the option to run a maximum number of iterations. That's helpful if you're doing a really big problem. You can let it run overnight, or you can say, just give me the solution after 100 iterations. So you can set a cap on the number of iterations it's going to run. This is likely though, because it's at 16, this is probably your optimal solution. The value of that early termination ability is, okay, that's not the optimal solution, but it's a suboptimal. And if computational resources are expensive for your problem or your company, you'd rather get a suboptimal, near optimal solution in say a couple days than rather than wait a month, especially if there's some sort of real-time processing software thing where they're collecting data in real time and need to give a solution. So that's a key thing. Know that you can early terminate most of the code, and it has a meaningful answer. I mean, there's some algorithms that you do an early termination. It may not make as much sense, but simplex certainly does. Okay, that was a tangent. All right, so back to this graph. So this iteration, what's happening when we have these stalls here? And this actually has to do with, let's take a look at the next page, page 254, this figure 5.7. So we've seen this figure before. Let's focus on this point here, x1. First of all, how many variables are in the original problem? This was one that we could graph in three-dimensional space. So there was actually just an x1, x2, x3. So n was 3 in the original problem, no matter what we've had to do to turn it into standard form or a possible auxiliary for a two-phase. But the original variables were x1, x2, x3. And x1 here is what is known as a degenerate basic feasible solution. And that happens whenever you have more constraints that are active than the minimum needed to define a point in that space. So to define a point in 3 space, we just need 3 constraints. And yet here we have 1, 2, 3, 4, 5 constraints, C, B, H, I, and G. And what that means, another way of thinking about this, is that the non-negativity constraints for some of your basic variables are active. In other words, some of your basic variables are 0. So it might be that you solved A delta X equals 0, and you're solving for the basic variables. And instead of all those being positive, you might have 1 or 2 that are 0. That's okay. It still maintains feasibility. But how it manifests, the fact that there's a 0, a basic variable that ended up being 0, is that you have degeneracy. And that, another way of thinking about that is that there are several bases, several sets of basic variables that actually refer to the same basic feasible solution. All right, so let's see what this means. So there's the summary of degenerate basic feasible solution. If you have more constraints active than needed, that means that your non-negativity constraints for some of your basic variables are active, which means some of your basic variables are 0. You solved A delta X equals 0 and got some of those were 0. It's okay, but it just means that there are alternative choices for the basic set. So if several of your bases can produce the same basic feasible solution. Okay, so we're going to think about this in terms of a few questions. So I'm going to pause and put a few things on the board. Okay, let's think about degeneracy with respect to these questions. What does degeneracy mean geometrically for the simplex? So we're at some basic feasible solution. We have a direction, and we're going to It turns out though that there's several bases that represent the same basic feasible solution. So we're going to have an entering variable, a leaving variable, get a new basis. And we think we're actually going somewhere and we're actually coming right back to that same one. So it thinks it's getting to a new basic feasible solution. But it's really the same thing. It's just a new representation of that same basic feasible solution because it's a new basic set, but yet it really gets you back to the same place. Well, what is that? And again, that's the plateau. So we think we've gotten to something new, but we're really at the same solution, which has the same objective function value. Right, well, what does that mean computationally for the simplex? It means that when you're doing your min ratio test, you could get a lambda equals 0. So again, we have a direction, we have a point, we have a direction, and we think we're going to go, but lambda is 0, and we really just end up right back where we were. So then we need to know, well, is this going to be a problem? Will the simplex ever escape this basic feasible solution? Yes. You just proceed as if lambda equals 0 is not a problem. So you're going to do another entering and leaving variable, just do another swap. And maybe you get lambda equals 0 again. There was that plateau in the previous picture where it happened 4 times. They tried 4 different basic sets. Something left, something entered. Still the same place, something left, something entered, still the same place, something left, something entered, still the same place, and one more time. But they eventually escaped, and that's the case. You just proceed as if it's not a big deal. So there are some more sophisticated methods for handling degeneracy, but for the most part, most codes, don't even worry about it because it will eventually escape. You could escape faster, yeah, maybe you recognize it faster, you can escape faster, but usually not a big deal. Okay, are there different levels of degeneracy? Yes, there are. And so let's go back to that figure and let's look at a couple. Let's see. Let's go ahead, share the screen, go back. This was page 254. 57. Okay, so on page 254, the same figure. Let's compare, let's say, x1 and x3. Those two. X1 we already determined was the degenerate basic feasible solution. X3 is also degenerate. 1, 2, 3, 4 constraints to find it, but you only needed 3 in this space. So X1 is actually more degenerate than X3 because you could get stuck there longer thinking you're at a new basic feasible solution. More lambdas equals 0. X2 is non-degenerate though, right? No problem there. Okay, so in terms of like preferred behavior, X2 is the best, X3, and then X1. All right, then one more question. Is it possible that the simplex could get stuck, plateauing 100 iterations? Yeah, it's totally possible. What it would mean is your problem is highly degenerate. I've worked on problems and they're not necessarily that big, but they have a great deal of degeneracy. In fact, you might think we'll have time this semester to see rankability, and we might have a homework associated with my rankability research where I create a integer linear program, a binary integer linear program, where nearly every basic feasible solution except a handful are highly degenerate. And so we're going to stall. Okay, so this section, just a few problems, numbers 25 and 28.